Hi, today we're talking about fusion and fission in regard to the Big Bang and the atom. So our first thing is we're going to go over the questions of what are the properties, byproducts, requirements, locations, energy release, as well as the advantages and disadvantages of both fusion and fission. First off, let's take a look at fusion. Fusion is when you take multiple things, primarily multiple hydrogen atoms, and you combine them together to make a new element. So if each hydrogen has one proton and you squish them together, you get helium, which has 2 protons. If you take 3 hydrogen atoms and squish them together, you get lithium, which has 4 protons. And then you also add your neutrons, and so you can make a great deal of elements. Also remember, with fusion, you are releasing energy as they are fused together. So some of the properties are your small atoms are getting bigger. Fusing mean being put together. The byproducts are non-radioactive materials. So when you fuse things together, you're getting new elements that are not radioactive. The requirements for fusion to be completed is high temperatures, very dense places with lots of energy. Primarily happens in suns and stars. The energy released in fusion is 3 to 4 times greater than that released in fission. Some of the advantages and disadvantages are it produces a lot more energy and has materials in abundance, and it's not radioactive byproducts. But the big disadvantage is it creates more and it requires more energy to get started, and it's very difficult currently to contain and sustain on the Earth. Fission, on the other hand, is the opposite of fusion. So fusion is creating, putting things together. Fission is taking apart or separating. So the big properties or definition of fission are large atoms breaking apart to get smaller. So when you think of radioactive decay, that's a fission. The byproducts are almost always radioactive materials. The requirements are high-speed neutrons and very little energy. This often happens in nuclear power plants. It does also happen naturally at some point in times during radioactive decay. That is a fission-like product, but the fission we are talking about is specifically processed with only radioactive materials. The energy release is millions times greater than chemical reactions. The advantages and disadvantages, it's very easy to sustain and contain. It's very doable right now, but unfortunately it produces radioactive byproducts and has limited resources for completion. Another big question are, what are the commonly used isotopes and what are their advantages and disadvantages, specifically for fusion and fission? So radioisotopes are used in a great variety of medical treatments. So for example, iodine-131, it's used to detect and treat thyroid disease. Technetium-99 is used to detect brain tumors and liver disorders. Phosphorus-32 is used to detect skin cancer. Cobalt-60 and cesium-13 are typical radiation sources for cancer therapy. So when we talk about radioactive isotopes and radioactive materials, a lot of times people think that it is only a negative topic, but a lot of these radioisotopes are used in medical technology to either treat or help cure certain diseases. So there are advantages and disadvantages to radioisotopes. Some of the advantages, they can diagnose and treat some diseases much more effectively. The fast-growing cancer cells are more susceptible to damage by the high-energy radiation, such as gamma rays, than the healthier cells, so it can be much more targeted treatment. But, of course, where there's advantages, there are disadvantages. And some of the disadvantages are they have negative impact on the healthy cells. They can burn them, damage, you can cause nausea. Some radioisotopes, it can cure one thing, but also cause cancer or other damage in others. Some cancer cells may be resistant to the type of radiation. It's incredibly expensive, And in large doses, often they give them in small doses, but in larger doses, which may be for treatment, it does negatively impact immunity and different resistances. It can isotopes or radiation can cause genetic mutation. When you think of radiation, you can think of the sun, and it gives you a sunburn. Your sunburn is the mutation of your cells. It doesn't get bad. They get more melanin. That's a very easy visualization for people to see. And the waste requires special disposal. I know when my son was going through some of his treatments, we had to be very careful in disposing of his diapers because we didn't want to handle the radioactivity. So what does the energy transformation of a power plant entail? Well, it's a nuclear power plant, and they go through. So water is heated by heat energy created through nuclear fission. So the heat energy that heats the water is through a radioactive fission reaction, and then the energy is lost to surroundings. So they're trying to contain it to the heat, but then you always do lose some energy. The steam from the heated energy turns a turbine, as that heat energy is transformed into kinetic energy, and at this point, energy is lost to friction. So right now we have 2 points where energy is lost. The heat energy is lost to surroundings because not all of it's contained in the water. And then energy is lost in friction and turning the turbine because you have to overcome that friction to turn the turbine. And then the turbine powers a generator. Again, energy is lost in friction in 2 places because you have to overcome the friction of starting of movement in order to turn turbines. And then from all of these processes, energy is transformed into electrical energy. So if you look at it, there's a beautiful diagram right here. You've got the containment structure that holds your rods, your reactor, and your steam generator. The steam line goes from your reactor to your turbine that powers it. You have a generator that goes out, and then you have a cooling condenser that cools the water. So, what is the connection between nuclear fusion and the evidence supporting the Big Bang? Because remember, this unit, we're all looking at everything through the Big Bang. So, we can use the processes that we see and learn here and see in evidence in the stars and support this idea of the Big Bang. So when we look at fusion, we really look at fusion supporting the Big Bang in 2 ways. The star composition. Hydrogen and helium really make up nearly all of the nuclear matter in the universe by mass. Hydrogen is 74% by mass and helium is 25% by mass. So the universe is 99% hydrogen and helium by mass. The heavier elements make up less than 1% of the universe. So when we look at that and we realize that hydrogen has 1 proton atom and helium has 2, we realize they really have to have been the building blocks of the universe because they make up so much of it. So hydrogen gets fused together in stars to make up everything else. So hydrogen is the building block of the periodic table. Now hydrogen and helium, the ratio in stars is a 3-to-1 ratio. And the relative scarcity of the heavier elements yield the critical clues about the density, temperature, and expansion rate of the early universe because they had to have been created later because there's so much less of them. Thank you so much about learning about fusion and fission.